Okay, peeps. So from the position problem, we should remember, and I want you to validate what I'm going to say with your notes. For the position problem, we propose the following vector loop equation. Sorry, vectors. We propose those three. We label them as R1, R2, and this was R3 and R4. Okay. So just as a recap, for position analysis, we end up having R1 plus R4 equal to R3. Yep, that was the vector loop equation. Okay, and I'm not going to solve it again, but we obtain these values, the magnitude of these two vectors, and that was, for R3 was 6.93 inches. And for R4 it was 3.46 inches. We also know from the position analysis that we said theta 3 was all that. Oops. That was theta 3. And theta 3 was equal to, what was theta 3 equal to?
300.
300 degrees. So that's from position. Now the new story starts. The new story is related to velocity. Okay. Now in this particular problem, they are giving me this data corresponding to velocity. You see, it says the velocity of AC, which means all this link here. I'm going to color that. That's link AC. The velocity of AC is equal to 10 inches per minute, acting at 180 degrees. That's what it means. It means there is a velocity of 10 inches per minute acting at 180 degrees. So it means it's acting this way. Yeah, 0 degrees is that one, right? And it says 180 degrees. So I'm going to stay with that. I'm going to make a slight change, a tiny change in the data of the problem, because I'm going to show you SolidWorks later. And in SolidWorks, I added this input velocity and it was very slow. And it demanded a very long time simulation. So I increased this by 10. So I have changed the input velocity. So input velocity to be 100 inches per minute. So change that. I just changed it 10 times. Okay. Didn't do much after that. Okay, if that is the input, so if the input is this, so basically they are saying me that that is the linear velocity of this vector. You see, they are related. This vector was telling me how far this point was from the origin. Now this velocity is telling me how quick that position is changing. So let's say then that this is my input velocity. This in is not from inches. STIN no es de inches, es de input, okay? And here I have the velocity analysis. What do you think is the output if this is the input?
The angular velocity of R3.
So the angular velocity of link 3, what else? Who said that?
Me.
Okay, yep, gracias Mauricio, what else?
The linear velocity of R1.
R1 is constant, I believe. R1 is just telling me the distance is, in fact, is these 6 inches here. So I don't think it's changing.
R4?
R4 is given.
I think Which one said Pablo Candelas? R1 or R3?
Pablo Candela said R1.
Ah, no. Entonces sí.
The velocity of the slider, maybe.
The velocity of the
magnitude.
slider. So there is one velocity that is telling me how quick this R3 is rotating, and that is omega 3, as it was said by Mauricio. And there is another velocity there because this slider is moving with respect to this point. Yeah, I'll show you the SolidWorks simulation in a second, but if you remember, this slider at some point is closer to this, yeah, and at some other instant of time is further away from it. So that is a change in linear position, which means a linear velocity. Let me jump to SolidWorks so that you remember how this thing moves. So once more, just for the fans, input velocity is given here. Two possible outcomes of this: how quick the distance from this point to this point is changing, and how quick this link is rotating. Just with one input, I control those two. Just now. So what do I do? How do I start? As I said last time, before the vector loop, let's think which type of vectors we have. So vector, magnitude, orientation. Who wants to help me with this table? Let's say R1. What about, which is the nature of R1, Pablo Candelas?
It's constant and constant.
Okay. Which is the nature of R3, Saúl Martínez?
Variable and variable.
Which is the nature of R4, Iván Muñoz?
Is se me fue la R que era magnitud, ¿no?
Yes.
Es variable y constant,
Good. Buen rescate ahí.
Question.
Yes.
The R4 has constant orientation because it is fixed with the box.
No,
Yeah,
it has constant orientation because it is down here, and this vector is representing how deep this point is getting into this wall. This is the wall, so the wall is restricting this link to move only horizontally. Yeah.
Yes. The word was restricted, not fixed, right? Because fixed would mean that it's like the R4 would be fixed to the box, but it isn't. It is restricted only.
It is R4 is representing the displacement of this link.
Okay.
Okay.
Thank you.
No problem. Okay, let's carry on. Now, my position vector loop equation was then R1, R4 equal to R3. If I derive that with respect to time, what do I get? Which vector will disappear from the velocity vector loop equation?
R1.
So I end up having only velocity vector 4 equal to velocity vector 3. That's all I have. Which is basically telling me that the velocity at this point is the same for both the one that is coming from R3 and the one that is coming from R4. That's what this vector is telling me. Okay, now let's think which type of vector this velocity vector will be. For instance, R4, which type of vector is R4? R4 is a vector which has variable magnitude, constant direction. And the vectors for this type was linear velocity, same orientation, as the position one. You remember? Yeah, that's the type of velocity vector for a position vector that has variable constant. ¿Sí? ¿Estamos bien hasta ahí? Esto lo vimos la vez pasada, ¿no? Okay, so I substitute this in the equation. I have linear velocity v4, cosine of theta 4, sine of theta 4. And all that has to be equal to whatever that is. And I don't know what that is. Which is the velocity vector for this type of position vector? I don't think we know it, right? We didn't do that on Monday. Sorry, today is Monday. We didn't do that on Thursday. Or did we? Sí lo hicimos en él. Paul
No.
dice que en él.
Nel,
Según yo no, profe.
Okay.
a ver si no.
So I'm just exploring new features of this thing. Be patient. Okay. Position vector then was magnitude, orientation. I'm not including any subindex. No le estoy poniendo R3 o R4 para derivarlo primero de manera general. Y ya que ustedes lo apliquen dependiendo de la situación. Now, this case is very particular because this bit is changing. And that bit is also changing. So if I want to derive that with respect to time, how do I do that? Any ideas?
Regla de la cadena.
Okay. Chain rule, if that's what you mean. Let's recap or let's remember this bit here. A function of x, sorry, let me do that a little bit thinner. It's too thick. A function of x, or any function, whatever. Let's say I have that, and I want to derive that. So the derivative of that thing will be equal to what? Differentiate the first one times the second one plus leaving the first one as it is times the derivative of the second one. You remember that? That's the chain rule. So let's chain rule, right? Que no lo entendía, pues qué aburrido. Ser del universo, ¿no? Okay. Now using the chain rule, how can I derive that? Well, first I'll leave the first one as it is. No, sorry, first I derive the first one and leave the second one as it is. So I derive the first one. You know, when you derive the magnitude, you end up with a linear velocity, right? Cuando derivamos la magnitud, nos quedamos con una v que es de velocidad lineal. Linear velocity times the second one as it is. Now I'm going to leave the first one as it is and derive the second one. Now what happens when I derive the second one? I'll end up having minus sine of theta times that. You remember? I hope you do. Plus cosine of theta, then deriving the angle with respect to time. What is this bit going to be transformed to or replaced with?
Your angular velocity.
An omega, angular velocity.
Okay.
Whenever Maritza is online, it's a different class. She makes my job more easier, ¿no? Hace mi chamba más fácil, Maritza. Thanks, Maritza, for joining us today. So this is a common factor between these two. So I can take that out. And then I have minus sine theta plus the cosine of theta. All this is the velocity vector for a variable case, which you can say, okay, so it is the sum of the two that we had before. Yes, it is. So far, it is. Okay. Now you just need to add the subindex and substitute in the equation. So I'll use this guy, use it here, and use it here. So it would be linear velocity 3 cosine of theta 3 sine of theta 3 plus the other bit, which is R3 omega 3 minus sine of theta 3 plus the cosine. And all that is my expanded version of the velocity vector loop equation. Questions so far? ¿Cómo vamos? ¿Se acordaban de la chain rule? Bueno, y si no, no es así que tú digas algo dificilísimo, ¿no? Okay. Now let's check what I know and what I don't know. Right? And let's identify the unknowns and try to solve this system of equations. So what about theta 4? Do I know it? Let's go back to the mechanism. Do I know theta 4? Which is theta 4? Which is the value for theta 4?
0.
0. 0 degrees. What about, and we did say that theta 3 was 300 degrees. And so it means that this I know. Lo voy a dejar en visto, ¿no? Como en WhatsApp. What about theta 3? I know it also. Lo dejamos en visto. Theta 3, I know it. Do I know R3? Now I know it, right? Theta 3 was one of the outputs of the position problem. So theta 3, now I know it. Of course, I don't know omega 3 and I don't know B3. We just said that those were the outputs. We say it here. So these are the outputs, the unknowns. What about B4? Do I know it?
It's the input.
It's
right?
the input. That's the input. Thank you, Gustavo. That's the input. Okay, this is just the guide for you to understand your notes when you're studying. Okay, let's substitute the values and solve for whatever I can work out. So the input, let's think about the input before we substitute. Input is B4. which is equal to minus 100 inches per minute. Why minus?
Porque va en el sentido negativo del.
Because it's going at, it's acting at 180 degrees. Gracias, Fer, Alonso. So it is negative because the problem was telling me it's acting towards the left. Okay, that's why I substituted negative. And also, there is something I need to do before substituting. What do you think it is?
Changing the inches per minute
Why do I need to change the inches per minute?
to second, inches per second.
That's right, but why? Because omega is in radians over second. I need seconds to be in the game. So that's right. Now change inches per minute to inches per second. And I've done that already for you, just for the fans, and I can tell you it is minus 1.66 inches over second. Now you can leave this as positive, but then when you substitute 100 0 here, if you substitute 180, it will change it to negative. So I think it's best to include the negative here, because theta 4 is 0. It's not going to make this negative. Let's split this into, no, let's substitute everything or split it. What would be easier? Let's split it.
Clear it.
I'm just going to substitute that guy acting horizontally equal to this unknown, and here I'll have cosine of 300 plus sine of 300 plus R3 was equal to what? What is the R3 equal to, pips?
6.93.
6.93. Okay, that's the substitution. Now I can split this into whatever happens horizontally and whatever happens vertically. So it means that it will be minus 1.66 equal to B3 times the cosine of 300. You can also get this value numerically. It's up to you. Plus 6.93 omega 3 times the sine of 300, and I think this has to change to negative, right? Okay, cool stuff. Now what about vertically? Vertically I have 0. Sorry, that was Sherlock waking up. That's 0, and I have B3 sine of 300 plus 6.93 omega 3 and cosine of 300 degrees. Those are my two equations. Okay. What is the, let's simplify this by doing some, by getting the numerical value of this. Can I borrow the calculator, please? Perdón, me presta la calculadora. Lo bueno es que sí me entienden inglés. Okay, let's do it. What is the cosine of the cosine of 300? 0.5. Yep. So then this bit here is minus 1.66 equal to 0.5 linear velocity of link 3. Oops. Plus, what is the sine of 300? Sine of 300, that is minus 0.86, is negative. So with this negative, it will become positive. Now just multiply this bit times 6.93. 6.00, so I'll say 6. Thank you, Pablo Candelas, for not abandoning me today. I know it's easier to abandon the guy that teaches you on a Monday. Let's go to this one. I have 0 equal to...
But the omega...
Oh, I'm forgetting the omega 3. You see? No me abandona. Thank you, Pablo Candelas. Sorry for not being perfect today for you. I promise I'll be better on Thursday. Okay, so sine of 300 was minus 0.8 something, right? Minus 8.6. So this will be minus 0.86 B3. We'll put one more decimal to be a little bit more precise. Cosine of 300 was 0.5, if I recall. Cosine of 300 times 6.93. That is 3.46 omega 3. Now, you can solve this manually. It's not hard. In fact, we can do it if you want. But let's solve it first. No, let's try to solve it. Let's try to solve it manually. See what happens. So, from this second equation, I can work out B3. So I'll say B3 is equal to give me a second. So B3 is equal to minus 3.46 over minus 0.066866 omega 3, which means this is equal to 3.99 omega 3. I can use that and substitute it there. Sorry, not there. Substitute it here and work out for omega 3. And using that, I get an omega 3 of, let me check with Guillermo. Yep, I get an omega 3 of minus 0.207 radians over second, which I'm going to convert already to degrees, because that's what the value of that I'm going to take from SolidWorks. And if I get this into degrees, it will be 11.9 11.86 degrees over second. And then I can use this omega 3 here again to obtain the velocity. Can anyone tell me the velocity, please? You just need to multiply this 0.207 and it will give you minus 0.83. This is inches per second. This is the solution by hand. Okay, let me change screen. Okay, I solved the system without substituting the values. So without calculating cosine of 300 and sine of 300. You see here, I have the two variables, B3 and omega 3, and I have cosine of 300 times B3. That corresponds to the horizontal part, yeah, cosine of B3, then minus 6.93 times the sine of 300 times omega 3, that is equal to minus 1.66. Yeah, you can check that, and that should be the first equation, the one on the acting horizontally. And then the second equation is sine of 300 times B3, 6.93 times the cosine times omega 3 equal to 0. Those are the two equations, right? And I can solve that. If I run this again, and then I say, tell me whatever B3 is equal to. Okay, I need to expand this. Minus 0.83, that's what we got, right? Let's check omega 3. Minus 0.2074, that's also what we got. So we're safe. Now we are only safe if we manage to validate this against SolidWorks. So let's do that, just for the fans, just because we have it. And I did the simulation here. I have added already the linear motor. Yeah, linear motor, you can add it from here. It will ask for a normal surface to which this velocity is going to be applied. And you can check that I try to put 1.6 inches per second, right? That's the input value. I don't need to put the negative sign because I have already included the direction here. Okay, easy stuff, nothing complex. Okay, the motor is there. I can run this bit. It moves as it should move. Beautiful stuff, pretty stuff, magical stuff, I'll say. And it becomes magical because I need to check the velocity. So this is angular velocity. Let me show you the graph. That's what I get. Okay, now which value is the one I need to check? Now you can do two things. You can check, because the angular velocity in degrees per second has to be minus 11.8. ¿Se acuerdan? Check your notes. We just solved that. Yeah, minus 11 point something. So let's check when it becomes minus 11 point something. So here is minus 13, minus 9. Let me see if I can make this bigger. So minus 11 should be probably here. Minus 11, but it's minus 11 point, almost 12 actually. Here is minus 12. It happens at 5.07 seconds. So if my solution is correct, which is the angle of this rotational link at 5.07 seconds? ¿Cuál tendría que ser el ángulo del elemento que gira a los 5.07 segundos?
30 grados.
100.
300 degrees or minus 60. Yep, because it's 300 or minus 60 degrees. So let's pray. Let's concentrate. Let's bring up the magic, because I also plotted the angular displacement. And I can go directly and check for 5 point something seconds. So here, .07 seconds minus 59. Boom. Take that, peeps. So it is correct, right? It is beautifully correct. It's not only correct, it is beautifully correct. So that, peeps, is just how you, that's only an example of how you create magic.